Hi, this is Ms. Frazita. We're looking at Chapter 3, Derivatives, and 3.1 is Derivatives of a Function. Okay, so before we get into that, I wanted to do a little bit of review with you. So what is a rate? Well, a rate is going to be a fraction, is kind of the simplest way I can say it. Oftentimes the bottom of the fraction is going to be time. So number 2, what is the dependent variable and independent variable? So independent variable is always your y and dependent is the x. And what is the most common independent variable? That would be time. So when you're looking at a graph, x and y, x is usually the time, whether it's hours or minutes or seconds, and y can be whatever it is that you're looking at. It can be distance or velocity, whatever. The graphs, I know that we've actually reviewed graphs quite a bit already, but looking at the 3 that I've put on here, I've got square root of x going from the origin on out to the right. ln of x, remember, has a vertical asymptote on top of the y-axis. And y equals e to the x, that's going to have a horizontal axis, a horizontal asymptote on the x-axis. Just good graphs to remember. Okay, so let's go ahead and talk about derivatives here. Well, if we go back to Chapter 2 in the last section, they really did foreshadow what was coming in Chapter 3. So the idea here, the main concept, is that you have a curve. Look at this black curve here. And the question is, what is the slope of the curve at a particular point? That slope of the curve at a particular point is what we will call the derivative of the curve. That's what we're going to spend probably the next 2 chapters looking at, the slope of the curve at a particular point. So from Algebra 1, the way we looked at slope was slope of a line, of course. We needed 2 points, and we would calculate slope with a change in y over change in x. So if we kind of go from what we remember in Algebra 1 and try to work with that, then if our goal, let's say, is to find the slope of the black curve at point P. So what we'll do is we'll introduce a second point, Q, and we'll look at the line that goes between P and Q. And if we're focused on the slope of that red line, then we know from Algebra 1 that it will be just change in y over change in x, or what I put over here as f of x2 minus f of x1 over x2 minus x1. And again, that's just the slope of the line that goes through P and Q, 2 points on the curve. So because it goes through 2 points on the curve, we call that a secant line. Well, the problem is, of course, we really want the slope of the curve at point P, not the secant line going through P and Q. So the concept is we take Q to be closer and closer to P, and then that red line that is our secant line will start looking more and more, maybe like this blue line, or even closer to P, it starts looking like a line that's tangent to the curve at P, which is really what we want. So by definition, the slope of a curve at a point is equal to the slope of the line that's tangent to the curve at that point. So again, as point Q moves closer and closer to point P, these secant lines that I have drawn here, both the red one and the blue one, they get closer and closer to approximating the line that's tangent to the curve at point P. So if I go ahead and calculate my change in y over change in x, looking at these coordinates that I've listed, then all I need to do is take the limit as h goes to 0, and that will force the point Q to be close, infinitely close to point P. What is h? So when I'm looking at point P, I've labeled it x1 and f of x1. Well, my point Q, if I slide it kind of close to P, how close is close? Well, we're looking at a distance of h away, and it looks like I forgot my subscript here. So it should be x sub 1 plus h. So however much x1 is, I move over a little bit in the x direction by the amount h. And this point here, Q, would have the x coordinate of x1 plus h. The y coordinate, of course, is just f of that. So when I plug in over here the change in y over the change in x, of course the denominator, the x, drops out, and we get our formula that we saw in 2.4. So just to recap, I put here at the bottom the main concept is that as the point Q gets closer and closer to the point P, the secant line looks more and more like the tangent line's slope. Okay, that is actually a huge concept. If you can understand all of that, you're pretty much set for most of the conceptual part for derivatives. Okay, let's go to the next slide. Okay, so this is kind of just recapping one more time, clearly important because I've put it in multiple times here. So slope of the tangent line is this one, and now this, instead of just calling it the difference quotient, which is what chapter 2 refers to it as, we're now going to call it the derivative. All right, so our notation for derivative is f prime of x. You see the little prime up there. And again, the limit as h goes to 0 means that point Q is getting infinitely closer to point P, so we have a tangent line. So here at the bottom I put note, this is also the slope of the curve at the point P when x is equal to a. So you see the a's in the equation. If I knew what exactly that point was on my curve that I was trying to find the slope of, I could plug in the x coordinate here and here for the a's. Okay. So while we're introducing derivatives, it's important to understand notation. And I have 3 common ways to write a derivative across the top here and 3 less common ways to write derivative. So the first one we would read f prime of x. This is y prime. And this one we just say dy dx. And then the bottom ones, this is df dx, or derivative of f of x with respect to x. And this is again derivative of y with respect to x. All 6 of these things mean the same thing. They all refer to the derivative of the function f. Okay, so let's take a typical example here. It says find the derivative of this function. And then in part B, find the derivative of that same function, but when x is 1. So again, think of derivative as the slope of the curve. So for part A, they just want us to get the slope of the curve. Now, as you move along the curve, and this happens to be a parabola, so as you move along this parabola, the slope is going to change from point to point. So what we're looking for in part A is a formula for the slope at any point on the function. And then when we move on to part B now we're looking at a specific place on the parabola when x is 1. What is the slope at that particular spot? Okay, so for part A, here's our derivative formula. And again, this is f of x. And if I want f of x plus h, remember I'm replacing the x's with x plus h. So I'd have 4x plus h squared minus 2x plus h plus 1. And again, that's what you see across the top. And then subtract, and then f of x. That's just our original function here in the parentheses, all over h. When I go ahead and square everything out and distribute my minus sign, I get this. And then I start canceling all my like terms. I get to here. At that point, all the h's in the numerator, I factor an h out and cancel it with the 1 on the bottom, and I get to here. And then finally, as my last step, I go ahead and take the limit as h goes to 0. In other words, plug 0 in for h, and that term drops out. I get 8x minus 2. So 8x minus 2 is going to be the general formula for the slope of my parabola at any x value that I feel like plugging in. On part B, they say, what about when x is 1? So I just go ahead and plug 1 in for x, and I get my slope at that particular point. Okay, a couple things that I should mention before I move on, just to make sure your algebra is going okay. When I subtract this f of x, all these terms that make up f of x, 99% of the time you're going to notice that they all cancel out with earlier terms. So this minus 1 has a plus 1 that cancels with it. The plus 2x has a minus 2x. The minus 4x squared after I distribute will be a plus 4x squared. All those terms drop out. So that's going to be the case for pretty much all the functions that we're looking at. So the second part of my formula up here, all of those terms that make up the f of x will cancel with something earlier. Now, also, after you do all that canceling, what's left on the numerator, or in the numerator, all of those should have an h in them. So every term on top has an h, and this will always happen. We factor the h out in front and cancel it with the h on the bottom. So until you get that h on the top and bottom to cancel out, you haven't really finished simplifying it, and you can't really take the limit yet. Okay, so little tips to remember. The second example, okay, this one is just straight up find the derivative if f of x is this equation. Okay, so here's my f of x. A little reminder of you, function notation f of x plus h. You're replacing the x's with x plus h's. Okay, so here's my equation for derivative. I start plugging everything in. Again, little tip that I gave you on the previous slide, the 5x squared will cancel with, I guess here, with this 5x squared, and this minus x will actually become a plus x, and it's going to cancel with the minus x here. So all the terms that made up f of x will cancel with something earlier. All the ones that are left will have an h in them. Factor h out of those common terms, or the common h out of those terms, cancel it with the bottom, and then go ahead and evaluate your limit. Let h go to 0. This term here will end up dropping out. I get my answer. So again, the 10x minus 1 is the equation for the slope of my curve at any particular value x. It's kind of like a handy little formula to tell you the slope of your curve. Okay, my third example, this time it says find the equation of the line that's going to be tangent to the curve at the point given. So again, we're looking at a parabola up here, and we have some point that's on the parabola. Oops, sorry. And so we're looking at trying to figure out the line that's tangent to this parabola at this point, and what is the equation of that line. This, by the way, is probably one of the most common calculus questions there is. Find the equation of the line tangent to the curve at the given point. You just memorize that one, guaranteed on the AP exam for sure, one of the multiple choice questions. Okay, so what I started with was the equation of a line in point slope form, and I plugged in my point 521, and I need to figure out my slope 10. Where did that 10 come from? Well, over here on the right, I went ahead and used my difference quotient, same as always, do the whole process. I got 2x. Remember, 5 is the x value, so we're looking for the slope when x is 5. I go ahead and plug 5 in, and now I get a slope of 10. So I plug my 10 in, I've got my equation of a line. Notice I use point slope form of a line. If you're still doing y equals mx plus b, you want to try to break that habit. This point slope form is what we commonly use in calculus. Okay, fourth example. Well, basically this is going to be one of those things that's a little tough the first time you see, but we're going to see it multiple times throughout several chapters. So the question is, given that this is the picture of the function, can you come up with a picture of the derivative? So the idea is we're looking at the slope of this picture in order to get the y-coordinates of this picture. So my top graph should have the y-axis labeled as f of x. The bottom graph should have the y-axis labeled f prime of x. My slope starts off negative, so I'm below the x-axis initially. At b, my slope is 0. If you picture a line tangent to the curve there, it's horizontal, so here I'm on the x-axis. And then my slope turns positive, and so I'm going up. And again at d, my slope was 0. Horizontal tangent line is slope of 0, so again at d, it's on the x-axis. And again, negative slope, 0, and positive slope. So below, on the x-axis, and above. Okay, so that was pretty quick. If that didn't make a whole lot of sense, don't panic. We see this multiple times, so this is just the first time you're kind of getting introduced to this. One-sided derivatives. Well, for a derivative to exist at a point, then the left side and the right side have to be equal. And if they're not equal, then we can only have a one-sided derivative. So I put in other words, the slope of a point only exists if the slope on both sides of the point are the same. Okay, so here the slope on the left of a point and the slope on the right of a point need to be equal. This is a concept that's going to carry over into the next section of our chapter. In fact, it's the main topic, so I'm not going to go into this too much detail right now. Okay, so here's our last example. And when you're looking at this graph of f of x, the question is, can you find f prime of x, and where is f prime of x not differentiable? So again, if you think of this as a corner right here, and this one's another corner, the slope to the left and the slope to the right of this corner are not the same. Therefore, this point has no derivative. Okay, same thing for the other corner. Slope here, it's not the same as slope here. Therefore, at that point, the derivative does not exist. So I know that this line right here, if I calculate rise over run, it's up 3 squares over 2. It's negative 3/2 for my slope in that interval from -1 to 1. And then across the bottom, of course, it's a horizontal line, so slope is flat. So between 1 and 3, my slope is 0. And then again, it's on the right side here, it's up 3 boxes over 1, rise over run, 3 over 1 is 3. So that's my slope over there. So I went ahead and drew my picture of my derivative. And at 1 and 3, the derivative does not exist. Okay, that's it. Thank you.